have our warm-up problem. Let S be the region x squared plus y squared less than or equal to 1, and x plus y squared less than or equal to 1. And I do hope that you know that is not the same thing. Those mean different things, right? So now, what do we have? Let C be the boundary of S. It's the boundary oriented clockwise. Find the integral around C, y cosine x minus e to the minus x minus y dx, plus sine x plus e to the y dy. And we have some various choices. Apparently pi might play a role in our answer. Do we have an answer? Did someone crack this nut, so to speak? Do we have a guess? Perhaps an educated guess? A? Good guess. You're only off by a constant factor. So, but I will say it's not A. Okay, well, let's think about this then. First off, let's talk about our region. We have two things that are describing it. This x squared plus y squared less than or equal to 1. Do we know what that is? Circle. It's not just any circle, it's the unit circle. Okay, so we can draw ourselves a unit circle. Okay. So let's pretend that's the unit circle, radius 1. And less than or equal says we want to be on the inside of our unit circle. Now we have another formula, and this one maybe is not quite so obvious, but let's think about it. X plus y squared less than or equal to 1. What does that look like? Ooh, line. Okay. That's actually, let's do the equality. So if you had x plus y squared equals 1, that actually leads to two possibilities. What are they? X plus y equals 1, or x plus y is negative 1. All right, negative 1. Good. These are lines. Can you tell me anything about this line, x plus y equals 1? It goes through, y-intercept is at 1. Slope is negative 1. So it's doing that. That's our x plus y equals 1. How about x plus y equals negative 1? What does that do? Essentially, it's very similar. It's parallel. The thing that's changed, where's our y-intercept? Negative 1. So it's doing this. Now, we want to have x plus y squared less than or equal to 1. What does that encompass? Because we have sort of three pieces. Where is x plus y squared less than or equal to 1? The middle part. So, if we have our region as both of these, then we can do a sketch. It consists of pieces of circles. So here's, I'm going to mark 1, minus 1, 1, minus 1. We have some straight line segments and some things which are quarter circles. Okay, so here is our region, S, because S is our region. Okay, the overlap, where both things are true. Now, C is the boundary of S. So we say, okay, great, C is the boundary of S. Which way are we oriented? Clockwise. And so we're oriented in the way that a clock would go. All right, now that's a lot of work for us just to understand the first sentence. Now we have to find the integral. How are we not going to do it? We're not going to do it by doing a line integral, because that seems like too much work. And one thing that they didn't write down, but they probably should have, I'll go ahead and write it down now, is because C is a boundary, it's a closed line integral. So what's our tool? Green's theorem. So whatever's in front of the dx, we call this m. Whatever's in front of the dy, call that n. Green's theorem says this is the integral over your region of n sub x minus m sub y. So that's just copying what Green's theorem says. What is the derivative of n with respect to x? Derivative of sine x? Cosine x? Derivative of x? 1. Derivative of e to the y? With respect to x? 0. Minus, now m sub y. What's the derivative of y cosine x with respect to y? Cosine x. Derivative of that, next term is 0. Minus 1. Well, what happens? The cosines cancel. Minus minus makes plus. So what do you have? Well, you really have 2 integral dA. So what is that finding? 2 times area. Well, think about your area. How much area do you have? Well, you have a triangle. How much area is in this triangle? A half. 1/2 base height. How about in this triangle? Also a half. How about in this quarter of a circle? Well, it'll be 1/4 of a full circle. How much area is in the full circle? Pi r squared. Radius is 1. So pi fourths and pi fourths, giving us pi halves. So if you multiply this all out, what do you get? Pi. 2 plus pi. Is this our answer? And why not? 2 plus pi is written down. So is this our answer? No. Okay, it's not our answer. Why not? Yes, our orientation's wrong. See, as we're walking along the curve, it's to the right. There's no song that goes to the right, to the right. It's always to the left, right? So the orientation's wrong. So what does that do? It changes the sign. So we have to fix the orientation. So we say, okay, go back through and throw in a fixing orientation sign. So what is the answer? E. Yeah, so be careful. We go out of our ways to be very specific about orientation. Make sure it's at the right direction where it's on the left, or is it the wrong direction where it's on the right? So pay attention, especially when you have multiple choice problems. They can be very tempting. Well, all right. Any questions? Okay. Let me finish what we did last time. So last time we introduced you to a device. I don't think they make them anymore. The Planimeter. And the idea was it's physically connected to a machine. And this is an analog machine, nothing, way before we had digital technology. It had a tip. You moved the tip around the boundary of the shape, and when you return to your starting point, you got the area. And how did it do it? It did a line integral. So this is an application of Green's theorem. And so we didn't do this problem. Find the area of the region bounded by the curve, and our curve is a cosine t, b sine t, where t goes from 0 to 2 pi. If you plug in 0 and you plug in 2 pi, you get the exact same value. And I'll go ahead and tell you it's already oriented correctly, so don't worry about orientation. So what should we do? Well, we were just told, here's how you find the area. So let's follow what the planimeter would do. Do a line integral. So we're going to integrate along our curve x dy. And we're not going to do Green's theorem. We're just going to do the line integral. So when you're doing a line integral, and you're actually going to do it by integrating with respect to t, what's the idea? You put everything in terms of t. That's the plan. That's what we're going to do. So what will our bounds for the integral become? We use the t bounds, 0 to 2 pi. What will the x become? A cosine t. What will the dy become? This is our x, this is our y. So for dy, take the derivative. So that would be, derivative would be b cosine t and dt. So this integral finds area. Well, a and b are constants, you can pull them out. And we're faced with the integral of cosine squared. An oldie but a goodie. We've seen this integral before. How do you integrate cosine squared? Trig identities. Yeah! Woohoo! Which trig identity? Because there's a lot of trig identities out there. We want to sort of reduce the number of trig identities we have to look at. Power reduction. So power reduction. Now it's on the formula sheet, but of course we also have power reduction memorized because it's such a cool formula. So that's 1/2, 1 plus cosine of 2t. Well, we integrate. So we have an ab over 2. The integral of 1 is t. Integral of cosine 2t, 1/2 sine of 2t. Evaluate 0 to 2 pi. We're almost done. When you plug in 2 pi, sine of 4 pi, 0. 2 pi is 2 pi. 2 pi times ab over 2. Well, the 2's cancel, so you get ab times pi. When you plug in 0, what do you get? 0 and 0. So our answer is ab pi. And we're done. Now on a side note, does anybody recognize this shape from the curve? It's an ellipse. So it's an ellipse where you go out to A in the x direction and out to B in the y direction. So that's the shape. So this is like, okay, so here's the formula for the area of an ellipse. That's a nice, pretty clean formula. Yes?
If A and B were the same, could it just be a circle?
Right, if A and B were the same, it'd be a circle. Now, are there easier ways to find the area of an ellipse? Yes, much easier ways. But this is one of them. So it's good to have. Okay, so that brings us to today, our thought for the day from a basketball player, Kobe Bryant. If you want to be a better player, basketball player, that's what that means, you have to prepare. Prepare, and prepare some more. So, of course, he was talking about how do you become a great basketball player, but it applies to everything. If you want to be a great musician, practice, prepare. You want to do well on an exam? Practice, prepare, and maybe prepare some more, right? You control how much you can prepare for things. It's a conscious choice. So make sure you put in the time. Make sure you invest. Invest in yourself. You're worth it. You're worth it. Now, what are we doing today? More practice with Green's theorem. And we're going to talk about surface area. And the reason we're talking about surface area is we're building up to the idea of surface integrals. So that's where we're going with that. Now, as far as surface area goes, I will say surface area, the important thing is to know that there's a way to compute it. So there's a little formula here that's on the formula sheet. And so we're really getting really close to the end. I think there's only 3 more formulas on our formula sheet that we haven't highlighted yet. The end is near. Okay. So, but first we begin with more things going on with Green's theorem. And we're going to talk about holey things, namely regions with holes. You can have holes and you can still apply Green's theorem. Everything still works. What do you have to do? You just have to make sure all the boundary curves are oriented consistently. And so that's why I prefer the notion of to the left, to the left. Some books will say, orient counterclockwise. But you have to be careful. What do you mean? Because you'll notice for the outside curve, yes, that's oriented counterclockwise. But for the inside curve, that's oriented clockwise. So that's why I prefer the notion of, okay, to the left. Now, why does this work? Well, there's 2 ways you can think about it. Subtraction might be an easier way to think about it, which is to say, imagine that the holes weren't there. And now, if you orient in the wrong way, right, orient in the opposite direction, you're subtracting something out. So it's an idea of subtraction. But I like to also think of it in a different way, which is to say, I can make what currently looks like several boundary pieces look like one boundary. One boundary to rule them all. One boundary to find them. One boundary to bring them all. And in the light of Green's theorem, bind them, as they might say. So, how do you do it? Just do a cut. So we're going to add a little bit of directions. And we're just going to move back and forth along this curve. So the idea, you move along the curve, move in, go around, move out, come along, move in, go around, move out, and go. And so by taking it, you can do one single curve. Now, here's the thing to observe. What happens if I go back and forth across this little piece? What's the net contribution of going back and forth? 0. And it cancels out. So that's why it works out. All right. So that's the idea. Well, let's try a problem here. Let's see be the union of 2 curves. The first curve is x squared plus y squared equals 1, oriented clockwise. And so we should probably draw that. Now, on a side note, you're probably wondering, why do we keep throwing in circles? There's 2 reasons that you'll see circles show up frequently in these types of problems. Reason number 1, a lot of times, if you use Green's theorem, you'll reduce it down to saying, oh, I just have to find an area. And it turns out we're really good at finding area of circles. Reason number 2, sometimes it's more than just finding area, but we can turn it into a polar integral problem. It's like, yes, 2 birds with 1 stone. We can double the fun. Okay, so our curve C1 is the radius 1 circle, and that's oriented clockwise. So that's oriented in that direction. C2 is x squared plus y squared equals 4. Again, a circle. Radius now not 1, but 2. So here's our x squared plus y squared equals 4. And that's oriented counterclockwise. And what's the question ask? Find the integral along the curve of 3x squared y plus y cubed dx plus 4x dy. So what do we do? Now, we could parameterize things and say, well, these are sines and cosines. Then we could have something like, oh, we get like a cosine squared or cosine cubed sine. You know, we get some powers of cosines and sines. But let's pretend we don't want to do that. We don't have to pretend very hard. Well, what's going on? These curves bound a region. So we can think of it as, oh, this is a region with a hole. Right? Because the orientation is consistent with taking the outside, where we're oriented to the left, and then the inside also is oriented to the left as far as with respect to our region. So we apply Green's theorem. So this equals, by Green's theorem, the integral over our region of, do you remember how it goes? N sub x, so whatever's attached to the dy, this is our n. And so n sub x is 4. Whatever's attached to the dx, which is this piece, is our m. So we took n sub x, now we subtract m sub y. So what is m sub y?
3x squared plus 3y squared.
3x squared plus 3y squared. All right. Good. Well, it asks us to find it. We haven't found it yet. We've just written it a different way. How would we actually go about integrating such a thing? And why would we think to do it?
Polar.
Polar! Why would we think polar?
Because I see x squared plus y squared with the same constant.
Okay, yeah. You see lots of x squareds plus y squareds. When you see x squared plus y squared, you start thinking, hey, that looks a lot like r squared. Think polar. If you're in 3 dimensions, you think cylindrical. Okay, so we're going to switch this to polar. Nice! Integral. This will become 4 minus 3. And if you factor out the 3, it's 3r squared. What does dA become? R dr d theta. Don't forget that r. That's important. And let's see, what else do we need? We need the bounds. Where does theta go from? 0 to 2 pi. Good. Where does r go from? 1 to 2. Okay, so before we integrate, we'll go ahead and multiply this out. So this becomes 4 times r minus 3r cubed. Okay, so Integrating. What's the integral of 4r minus 3r cubed? 2r squared
3/4 r to the fourth.
minus 3/4 r to the fourth. Evaluate 1 to 2. And I should say this is r equals 1 to r equals 2. Well, we plug in 2. What do we get? We'll get 0 to 2 pi. 2 times 2 squared is 8. 2 to the fourth, 16. 16 times 3/4? 12. So 8 minus 12. Subtract 2 minus 3/4. Now, the good news is this is going to be a super easy integral once we actually carry it out. We're going to get some negatives, and that's okay. You can get negatives. 8 minus 12, that's minus 4, minus 2. So these pieces combine to minus 6. Then we're going to have a plus 3/4. That's minus 24 over 4 plus 3 over 4. Or that's minus 21 over 4. So what's our final answer going to become?
21 pi over 2.
Yeah, so when we integrate, we get minus 21/4 theta from 0 to 2 pi. And we plug it in. We plug in the 2 pi, get minus 21 pi over 2. All right, cool. Any questions? Okay, so interpretations of Green's theorem. What's going on? Well, there's two ways to think about what's happening with Green's theorem. There's a circulation interpretation and there's a flux interpretation. And both of them have a role to play. So you have F as a vector field. So that's the arrows that you see here. So remember when we talk about a vector field, it's a vector valued function. And we can oftentimes visualize it or think of it as at every point there's a vector associated with that point, pointing in the direction that's associated with the vector at that point with a certain magnitude. So this vector field looks like you're sort of expanding from this point over here and you're collapsing over there. Well, there's lots of things it could be. We have our curve C, and I've shaded in the region. So, what's going on? Well, circulation says, move along the curve and ask the question, how much is a particle being pushed or pulled as it travels along the curve? So that's the circulation. So the more it's being pushed, the higher the number. Let's say it's positive, it's being pushed. If it's being pulled, maybe we'll say it's negative. It just depends on interpretation. How do you compute that? Well, what you're looking at is you're saying, what's happening to a point in the direction of motion? So you want to look at F dot T. So that's with motion. So how much is the force affecting your motion? Well, that becomes your mn dot dx dy, which is your mdx plus ndy. Classic Green's theorem. And as we've already noted, we said, oh, you know that part of Green's theorem looks familiar. It kind of looks, suspiciously, like a piece of the curl. And we're going to say this is foreshadowing. This is after the break, what we're going to talk about. Say, what if, instead of being in the plane, we have something in three-dimensional space? Well, then it's going to look a lot like this. All right, now, the other thing is flux. Now, flux is another way to say flow. I believe flux is Latin for the word flow. So the question becomes, okay, how much is flowing through the curve? So how much passes through the boundary? So what do I want to look at? Well, I want to go along the curve and I want to total things up, but I'm not going with motion. Where do I go? I go perpendicular to motion, and we do outward pointing normals. So for each point along the curve, I look at the outward pointing normal, and I'm saying, let's look at f dot n. So f dot n gives me information about how much is coming in or going out. So I could say, oh, if this sum total, say, is positive, I say, oh, things are flowing in. If it's negative, I could say things are flowing out. So how do we find this? We integrate along the curve of f dot n. Now that sounds harmless, but we have to think of, well, how do you find n? It turns out it's dy comma minus dx. How does that work? Focus, for example, on this part right here. Think about what's happening at the top. As I come along the top, what's happening with our change in y on the top part? It's basically 0 because I'm on the top. So it says, okay, I should have no change in the x direction. But now, what's happening to change in x? Is it positive or negative? As I'm moving here, it's negative. So minus dx would be a positive thing. So that's why you see this minus dx in the y direction and dy in the x direction. If you test a few points and see what's going on, you'll see it's consistent with an outward normal. Well, okay, so you do the dot product. So you have minus n dx and plus m dy. And this is where it becomes sort of like, alphabet soup. You have to think about things. So the rule for Green's theorem says, whatever's in front of the dy, what do you do with it? Take the derivative with respect to x. So in this case, m is what's in front of the y, so it's m sub x. Then you subtract whatever's in front of the x. What are you supposed to do with it? Derivative with respect to y. So you're going to subtract minus n sub y. Well, turns out, using advanced marker technology, minus minus is plus. I know. True story. So this is mx plus ny, ny, also known as the divergence. So, if I want to compute flux through the boundary, it's the same as computing divergence in the interior. We're going to talk about a generalization of this to higher dimensional objects after the exam. It'll be our last topic. So these are previews of our last two topics. We're basically going to take these two ideas, which are for Green's theorem in the plane, and say, let's generalize these to 3 dimensions. So that's where we're going. So let's try this out. Here's a curve. So it's consisting of 3 pieces. All of the arcs are half circles. So I have a half circle, another half circle, a big half circle. Find the flux, or the flow, through C for this vector field. xy squared over 1 plus y squared I plus y sine x cubed plus arctangent of y j. This will be fun. Good times. And you should be comfortable with using it in either component form or ij form. If you prefer component form, this is the exact same thing as xy squared over 1 plus y squared comma y sine of x cubed plus arctangent of y. So, we see flux. We just talked about flux. And we have our curve C. I didn't label it, but I'll go ahead and throw a label on it. What can we do to compute flux through a closed curve? we can, of course, integrate along the closed curve of f dot n. However, that would be unpleasant. We don't want to do that. So what can we do? Well, we can apply our Green's theorem tool and say, look, let's, instead of doing that for that shape, let's work over our region. And it says this is the same as the integral over our region. Do you remember what goes here? You just mentioned it a minute ago. Sorry, what? Can you say it again? Divergence. Yes. So if you see flux, think divergence. So that's going to be a clue for the final. If you see flux, think divergence. All right. We haven't written the final yet, but I suspect there will be a flux type problem. So what do? Well, let's compute the flux. What's the flux? So integral r. So we have to remember how to take a flux. We have our pieces m, our pieces n. So what do we do with the first part? What are we taking the derivative with respect to? Did you say why? Well, the reason I'm asking is we need to know. And no, the answer isn't y. It's x. Because divergence is the nice one. It says you take the derivative in the first slot with respect to the first variable, take the derivative in the second slot with respect to the second variable. So the first slot is the x slot, second slot is the y slot. So it's m sub x plus n sub y. That's what we're taking. So you have to be careful. So that's why it's a little different. So what's the derivative of this with respect to x? Spoiler alert, it's a lot nicer than taking the derivative of this with respect to y. Yeah, y squared over 1 plus y squared. Now we come to this term. What's the derivative of this with respect to y? Sine of x cubed and 1 over 1 plus y squared. Okay. So, how are you feeling? Optimistic yet? Are we going to make it? Yeah, we're feeling good. Is there anything we can do to make things simpler? Well, what do you notice about those pieces? Same denominator. If we add them up, what do you get? 1. So we have the integral over region. Some sense says split up, so I'll go ahead and split up. Integral over region of 1 plus, unfortunately, there's another piece, sine of x cubed dA. Now, one of these integrals is straightforward, but the other integral is also straightforward. All right, so which one should we do? The straightforward one or the other straightforward one? The other one? Okay. Well, actually, I'm not sure which one you think is the first one versus the second one. Let's talk about this second one. It looks terrible because this is a very unusual looking function, a very strange looking function, a very weird looking function, a peculiar function. Some people might even say what? It's an odd function. Now you might say, okay, what does oddness do? Oddness says what? If you look at a little piece on the right-hand side versus a little piece on the left-hand side, what happens? They're symmetrical, but what happens to those pieces? They cancel. So oddness, odd we like is that's, if you remember, that's when you have this going on. So a little piece over here will cancel with a little piece over there. But it works anytime you have symmetry across in the x direction, so across the y-axis. So what happens to the second integral? Goes to 0. So we can take advantage of being odd, goes to 0, since sine of x cubed is odd plus symmetry. Yes? You have a question? Or?
What made sine of x cubed odd?
Sorry, what?
What made sine of x cubed odd? Is it just the fact that it's degrees odd?
Well, it's part of it. But what does it mean to be odd? Do you remember? Okay, so odd says if you plug in the negative, then the output is negative. So if you put the negative x in, negative will be at the outside. So let's start with the cubed. If you take negative x, the whole thing cubed, what happens with that minus sign? It's still there, right? It's minus times x cubed. Now think about sine. What's the relationship between sine of a negative angle and sine of a positive angle? The same magnitude, just different sign. They differ by a minus sign. Sine is an odd function. So a composition of odd functions is odd. And put another way, what we're saying is that sine of negative x cubed is negative sine of x cubed. So whatever the value is on this piece over here is the opposite sign. So when we think of chopping up, we say, oh, if we just pair pieces up across the y-axis, we get perfect cancellation. This other piece, how do we do this integral? It's area. Well, what do we have? These are all half circles. So how big is this piece? Well, think of it as take a big half circle. So what's this area? Yeah, it's 1/2 pi. What's our radius? 2. So 2 squared. Subtract. Now we have to take off these pieces. Well, if you put these two circles together, you'll make one whole circle. What's the radius of that circle? It's the radius 1. So what's our final answer? We end up with 2 pi, subtract pi. So our final answer, this problem, easy as pi. Nice. Pi, classic pi. Okay. Last idea for today. We want to talk about surface area. Just the only thing you have to remember is this punchline. But we'll talk through the idea. So we want to find the total amount of surface area, and we're going to do a very special case. We have a surface described by z as a function f of x, y, and we're sitting on top of some region R. And we say, okay, well, what happens? Well, it can be a little bit wrinkly up here. So what do? Well, we do what we always do. Break things into small pieces, figure out what's going on, and add it back up. So we say, all right, we're going to chop R into little tiny pieces. So we're going to grab a little tiny piece of R. So this little tiny piece of R, there's our little tiny piece of R. And in the meantime, we're going to get a little tiny bit of surface right above it. So there's a little tiny bit of surface right above that little tiny piece. So I'm zooming in, just saying what's going on. Well, because we're small, what happens is that down here I have a rectangle. Upstairs, it will be sort of almost like a rectangle, but it's been slanted a bit. So it's almost a parallelogram. So it's a parallelogram-ish. It's approximately that. I say, okay, well, let's do more than just approximately. We can say, let's imagine I take the tangent plane, and so I can use that to find a good parallelogram that's a good approximation to that bit of surface. Well, the sides of the tangent plane, we have changes in x downstairs and changes in y. Upstairs, we say, well, up here, we're going to change in x, the z part changes according to the derivative of f with respect to x. Similar here, you have change in y, so you have change in y, and then the z part changes according to how much f changes with respect to y. And once again, we say, we have a way to find area of parallelograms. We've crossed this bridge before. We can use the cross product. So we take the cross product, and then we take the magnitude. So I skipped doing the computation. It's not a very exciting one. But then the magnitude becomes the square root of 1 plus f sub x squared plus f sub y squared delta a. And so that's your little bit of area. That's just for a little tiny piece. To get the whole thing, add them up. So the total surface area, we're adding them up over our region, are little bits of surface. So this expression, the square root of 1 plus f sub x squared plus f sub y squared dA, that's what I call DSA, a little piece of surface. Now, in practice, this leads to really unpleasant integrals with about 2 or 3 exceptions. And so you're like, okay, so does that mean all surface integrals get unpleasant? Well, good question. Turns out there's a nice case when we have 2 terrible things canceling out. And we'll talk about that next time. And we'll stop here for today.